Okay, so for our last talk of today, which is a shorter day than the next 2 days, we have Teng Fei from Rutgers, who's going to tell us about deformations of geometric structures. Oh, no, symplectic deformations and the Type IIA flow.
Thank you, Tristan, for the introduction, and thank you also for the invitation. It's a great honor to speak at this occasion, in memory of Professor Kuranishi. So today, I'm going to talk about simplex deformations and the Type IIA flow. So here's the outline of my talk. So all these projects are based on 4 papers we put on archive. The first one has already been published. These are joint work with Phong, Sebastian Picard, and Xiang and Zhang. So Phong and Picard, they are both here today. So I'll begin with some backgrounds of this talk. So that is basically what is the Type IIA flow, and then I'll state our main results. And then I'm going to mention some applications of our flow and some examples. And finally, if we have time, then I'll also give a sketch of our proofs. Okay, so let me begin by saying a few words about Professor Kuranishi. So as you can see, I'm too young, I guess, to meet Professor Kuranishi in person. So I can only get to know him through his work. And actually, Professor Granishi didn't write very many books. I happen to have these 2 books of him, and there's some story behind it. So when I was a postdoc at Columbia University, that's in 2016, Professor Granishi has already returned to Japan. But still, I see the legacy of Professor Granishi at Columbia very well. Actually, the graduate students there informed me that when Professor Granishi left, he left all his mathematical books at the graduate student office, and they are free to pick up for everyone. So when I went there, I got the book on the left, and recently, so this is about his famous result of a prolongation theorem. And recently I learned this is actually known as the secret notebook, the San Paulo notebook, which is a rare one to get. And the one on the right, of course, is his famous result on deformation of complex structures on universal families. And this has something to do with my talk today. Okay. So let me begin with deformation of complex structures, which are also the topic of Professor Boisson's talk today. So here now let's fix a compact complex manifold X. And following the work of Kahler, Spencer, Nirenberg, Kuranishi, and many others, we know quite a few things. So first, we know the infinitesimal deformations can be identified as H1 of the tangent sheaf. And also there's a primary obstruction lives in H2. And when H2 is 0, there's no obstruction and the local moduli space is smooth. And in the general case, we have the Professor Kuranishi's famous result about existence of universal families, now known as the Granishi families. And as mentioned in Professor Boisson's talk today, that if X is a Calabi-Yau, which means the canonical bundle is trivial and also it's Kahler or just satisfying the DD bar lemma. Though in this case, H2 might not be 0. However, the deformation theory is still unobstructed, so we get the moduli space is smooth. And in fact, mirror symmetry predicts that this moduli space of complex structures encodes the symplectic geometry of the mirror mesh. And we know that for this Calabi-Yau manifold, there are Kahler manifolds. So there's a symplectic side and there is a complex side. So you can ask, okay, if we know if the central fiber, say X is Kahler, And we have some deformation of complex structure. Are those deformations still Kahler? And the answer turns out to be yes, which means there's no additional obstructions of Kahler structure if you already have a deformation of a complex structure. And somehow guided from this duality or mirror symmetry, you can ask similar questions about symplectic deformations of Kahler manifolds. And these kind of question seems rather trivial in a sense, because if you fix a compact Kahler manifold, you consider the deformation of the symplectic form, then you're deforming in a linear space, which means there's nothing, there's no obstruction. And by Moser's trick, so you can modulo the action of the diffeomorphism group, and you can see the infinitesimal deformations actually can be identified with the second theorem cohomology. So there's no obstruction at all. But then you can ask the questions just guided by the complex case, whether nearby deformations are still Kahler. So you start with something Kahler, you have a deformation of the symplectic structure, and you ask the nearby symplectic manifolds, are they always Kahler? And the answer is yes, if you're only deforming the cohomology class in the H11 direction, because in that case, you don't even need to deform the complex structure, you can use the same one. And surprisingly, I cannot find many references in the literature. The only one I can find is one paper by de Bartolome in 2005. And basically, he argues that in general, there's some obstructions to be expected. Okay. And another question we may ask is that if X is a Calabi-Yau, if we begin with a Calabi-Yau, is there anything special we can see, like the BTT theorem, the Bogomolov-Todorov theorem? Is there a symplectic version? Okay. And it turns out by using the Type IIA flow we introduced, we're able to show this, demonstrate the symplectic version of the BTT theorem. That is, this Kahler property is stable under symplectic deformations for Calabi-Yau three-folds. And moreover, is that our proof actually works at the level of the form. So we don't have to quotient out this diffeomorphism group action. And it's a very straightforward argument. However, this is really not our original motivation to introduce this Type IIA flow. As you can see from its name, that this Type IIA flow comes from string theory, more precisely the Type IIA string theories. So let me say a few words about string theories, especially superstrings. So string theories, there are some 10-dimensional theories, which means they build on 10-dimensional Lorentzian manifolds. And besides the manifold itself, there are various fields, which you can think of as some sections of certain vector bundles over this manifold. And they satisfy a complicated differential like PDE system. Okay, and there are 5 kinds of them. They are called Type 1, Type IIA, and Type IIB. And they're hadronic strings with 2 different gauge groups. So in general, they are quite complicated to describe and to study. Okay, so to get a better understanding of them, we need to make some simplifications. And there are a few ways to make life easier. First, you can impose what is called the supersymmetry, which is the exchange of fermion and boson. And in terms of math language, you may think of this. This means there exists certain spinor satisfying a first order PDE. It's the killing spinor equation. The second thing we can do is called a dimensional reduction or compactification. Because we're working with a 10-dimensional theory, but our physical life physical experience tells us there's only one time direction and 3 spatial directions. So we break our 10 manifold into 2 pieces. One is 4-dimensional, for example, a Minkowski spacetime, and the other piece is the Riemannian manifold X. And we try to reduce the PDE system to some equations on this 6-manifold X. And finally, we can also impose this flux-free condition. Roughly speaking, it means some of the fields are 0. So in this celebrated paper by Candelas, Horowitz, Strominger, and Wheaton, so they impose all 3 conditions. And they show that the 6-manifold X is very special. It has to be a Kahler manifold with Ricci flat metric, and they call such manifolds Calabi-Yau manifolds. The reason is that this Ricci flat condition is equivalent to a complex Monge-Ampere equation first solved by Yau. And this is the Calabi conjecture. And in this case, what we get is the following data. We have the manifold X, 6-dimensional. We have a Riemannian metric G. We have a complex structure J, which is integrable. We have the Kahler form, omega, little omega, that's closed. And we also have this holomorphic volume form, capital omega, which is parallel under the Levi-Civita connection. And this is known as an integrable SU3 structure. This is very nice. However, for realistic considerations, especially from particle physics, in general, we cannot impose the flux-free condition. So we have to give up these requirements. And if we still impose the other 2 conditions, that is supersymmetry and this dimensional reduction, we get so-called supersymmetric flux compactifications. So, and because now we have less constraints, we are getting a more complicated system of equations on the 6-manifold X. And in the case of heterotic strings, this is known as the Howe-Strominger system, discovered independently by Howe and Strominger. And in the case of type IIA and type IIB strings, in math literature, these equations were first written down by Tomasiello and Tseng and Yau. So I'll say what they are, especially for the type IIA equations in my later slides. But the key thing I want to mention is that because now we have less constraint, usually what we get is a non-integrable SU3 structure. So it's still an SU3 structure, but it's not fully integrable. They are only partially integrable. In the case of heterotic strings and type IIB strings, we're in the world of complex geometry. So the complex structure is integrable. However, the metric may not be Kahler. And in the case of type IIA strings, we are in the world of symplectic geometry. So we have a closed symplectic form. However, the almost complex structure may not be integrable. Okay. So in general, you can ask for SUN structure instead of SU3 structure because we know Yau's theorem works in any dimension. And for SUN structure, you have the manifold X, you have the Riemannian metric G, you have a compatible almost complex structure J, and also you have this fundamental form, like little omega. So this is an almost Hermitian manifold. And then you also have this smooth section of the canonical bundle with respect to your almost complex structure, and it's nowhere vanishing. It's like a complex volume form. And to describe this SUN structure, actually, you don't need everything I put here, because from J and the little omega, you can recover the metric G. And from the complex volume form capital omega, you can recover the almost complex structure J. So you only need little omega and the capital omega to describe everything But there's something special for SU3 structure. That's some algebraic miracles in dimension 6, which was explaining actually Professor Donaldson's talk last week, and also in Professor Hitchins' paper, and also Robert Bryan's work. So the miracle is that in dimension 6, this imaginary part, which I call phi hat of the complex volume form, is uniquely and canonically determined by its real part, phi. And because of this, then in this dimension, we only need these two things, little omega and the real part, phi, to characterize an SU3 structure. And with this understood, we can give the type IIA equations. So there are 3 equations. The first one says both omega and phi, they're closed forms. And second says phi is primitive with respect to omega. And this is a very natural condition, because if you think phi determines the almost complex structure and omega should be a 1-1 form with that, then this is automatic. And the third equation is the key player of my talk. It's a second order PDE. So we have from phi, we have this algebraic construction to get phi hat. And we can also define the norm of phi squared by that's phi norm squared times the volume form of this symplectic form is given by phi wedge phi hat. So that's what's inside the parentheses. And this lambda is the contraction with the symplectic form. So we have d lambda d, which is something, it's a source term I call rho A. And for my talk today, you can just treat rho A as 0. Doesn't matter. But in general, this term is actually singular. It's actually the Poincare dual. It's a current, which is a Poincare dual to some combinations of special Lagrangians. Those are calibrated by the 3-form phi, because phi is closed. And from the pioneering work of Harvey and Lawson, we know that it gives us a calibration. And so you can discuss the special Lagrangians with respect to these 3-form phi. Okay, and if you know something about so-called symplectic Hodge theory, then this second order operator d lambda d can also be written as partial plus, partial minus. This is the symplectic analog of the dd bar operator in the complex geometry, and it maps primitive forms to primitive forms. Okay, so this is the type IIA equations. And another important thing about dimension 6 is that we have the stability of phi in the sense of Hitchins, which means that if you deform the 3-form a little bit, and it is still the real part of a complex volume form. In other dimensions, this orbit of real part of a complex volume form will be closed. It's like a high codimension thing. So when you deform a little bit, you may be away from this orbit. And but in dimension 6, it's an open orbit. And in that case, we can use geometric flows to study this system of equations, because geometric flow tells you a way to deform your, say, the form. And in this case, you don't have to worry about these equations are not going to make sense after small perturbation. Okay, so these are the, this is the equations I'm going to talk about. And before introducing our flow, let me say a few words about what's explained in Hitchins' paper, that is how to construct this imaginary part from the real part, because this is a really very nice construction, and it will be used over and over again in our work. So this is purely linear algebra. So we fix a 6-dimensional oriented vector space over real numbers. And then we can consider a 3-form over it. Using this 3-form, we can define, sorry. Okay, so using this 3-form phi, we can define a linear map k phi from V to V tensor to the top form. By if you input a vector V, then you take an interior product with phi. So you get a 2-form, and you wedge with phi again, you get a 5-form. And you can identify the space of 5-form with V tensor, the top forms. Okay, so you get this linear map k phi. And you can compose it with itself. Then you get a map from V to V tensor the top form square. Of course, this can be done in any dimension. But in dimension 6, the miracle is that this is k phi square is always a multiple of identity. And you can write this multiple lambda phi as 1/6 of the trace of this map. It lives in the top form square, space of top form square. This is like a line bundle or a line. And when this number or this multiple is negative, which means minus of lambda phi is a square of a top form, then you can normalize k phi suitably to get an almost complex structure, J. And then you use J to pull back the real phi, you get the imaginary part, phi hat. So the phi plus I phi hat will be a nowhere vanishing 3-0 form with respect to this particular almost complex structure. So here, everything is canonical. The only way you need the orientation is just to take the square root of minus lambda phi. You need to take the positive square root. Otherwise, you don't even need the orientation. And we see that this condition lambda phi is negative. This is an open condition, which tells us the orbit or such phi forms an open set. And this construction works well if you have a symplectic form. And you can show that if the symplectic form is invariant under this almost complex structure, which means it's a 1-1 form, if and only if the 3-form phi is primitive. Okay. So now we're going to talk about this Type IIA flow, which is, we can think of it as a parabolic approach to solve the Type IIA equations. There are two unknowns, omega and phi. And what we are trying to do is to fix the symplectic form, omega, and try to flow the 3-form phi, such that the last equation can be solved. And to be more specific, so this is our flow. We fix the compact symplectic 6 manifold x omega, and we want to solve the evolution equation. dt of phi is basically what we want to be 0 in the last equation. And of course, we have these first 2 equations to solve as well. So we need to impose some condition for initial data. That is, initially, these 2 equations should be solved. And the hope is that the primitiveness and closeness of the 3 forms will be preserved under the flow. If that is the case, then if the flow converges, then it will converge to a solution to the Type IIA equation. So this idea really comes from anomaly flows introduced by Phong, Picard, and Zhang. Okay. So before explaining what we proved, let me mention some features of our flow. So first, this is a flow of 3 form. And there are also other notable flows of 3 forms in G2 geometry. For example, there's Bryant's G2 Laplacian flow. And actually, there's some connection with our flow, with the Bryant's G2 Laplacian flow. And secondly, from the construction Hitchins explained, so the flow of the 3-form phi will naturally induce is the flow of the almost compact structure J. therefore, we can use our flow as a way to find optimal almost complex structures on a given symplectic manifold. And you are going to see some examples later in this aspect. And in literature, there are other flows like this. For example, there's an anti-complexified Ricci flow by Le and Wang. And also there's Wei Yonghe's D star D flow. And they also have some connection with our flow as well. And third thing is that this is actually a rare scenario in symplectic geometry that we can produce intrinsically defined second order like elliptic operator, because we know symplectic geometry locally it's very flexible. There's no local invariance. It's very hard to get an elliptic operator like this. And the fourth thing is that at least formally, it preserves the closeness and the primitiveness. And for later convenience, we call such thing type IIA structures. So a type IIA structure is just a triple where M omega is a symplectic 6 manifold together with 3 form phi that is closed, primitive, and positive. So closed, this is like a differential condition. Primitive is a purely algebraic condition. And the positive here means two things. So first, this lambda phi is negative, so you can do the Hitchins construction I described. And second, from that construction, you get almost complex structure J, and you want the metric you produce from symplectic form and that J to be positive definite. So anyway, the positive is an open condition. So if you have such a thing, we call it a type IIA structure, and formally at least, the flow preserves the type IIA structure. And finally, there's similar equations in the type 2B strings, and you can introduce the similar flows there. And you can show that these two flows, actually, they are T-dual to each other under semi-flat reduction, which is expected. Okay, so now let me state our main results. So from now on, we're going to concentrate the source-free case, which means the row A is 0. And this is not a big issue because in general, this term is a current that is Poincare dual to some special Lagrangians, which means they're like delta functions supported on this special Lagrangians. So they are 0 away from this locus. Okay, so this is like the simplest case. Okay, so this is the system of equations we want to study. And the first theorem is really a basic one. That is, this flow has short time existence and uniqueness, and it preserves the type 2A geometry. And our second theorem is a convergence result. So it says this flow preserves the integrability of the almost complex structure. That is to say, if you start with some initial data whose corresponding almost complex structure is integrable, then along the flow, the complex structure, though it's evolving, it stays integrable. And in this case, the flow converges to an integrable SU3 structure, which is a Ricci flat Kahler metric. And in this case, the flow actually is gauge equivalent to the inverse Monge-Ampere flow introduced and studied by Cao Kahler and Collins, Hisamoto, Takahashi. You can think of this result as an analog of the Calabi-Yau theorem in the symplectic setup, because in the Calabi-Yau, original Calabi-Yau theorem, what you do is you fix the complex structure and you deform your scalar form in the cohomology class, then you show you can make it Ricci flat. And in our case is that we fix the Kahler form omega and we can deform the complex structure along the flow to make the metric Ricci flat. Okay, and the third result is a classification of stationary points and also compact steady solitons. So this is parallels with the story of Ricci flow. So it turns out this classification just gives you a Ricci flat type IIA structures. If it's a soliton, then it also comes with a Killing vector field. So here by a soliton, I mean, you just add a Lie derivative term to the equation. And because both phi and omega, they are closed. So by Cartan's formula, only one term is meaningful there. So you get this soliton equations. And the Ricci flatness means that there's a type IIA structure that such that the complex structure is actually integrable, which gives you a Kahler metric. And also the phi norm square is a constant, which gives you a Ricci flat Kahler metric. And the Killing vector field simply means the Lie derivatives of phi and omega are 0. And again, we only have this one term there. And the fourth result shows that our flow is dynamically stable near its stationary points, which are the Ricci flat type IIA structures given in theorem C. And so the more precise statement is that if we fix a Ricci flat type IIA structure, then for any nearby type IIA structure sufficiently close in the subleft norm, WK2, in this case, we are allowed to deform or to change the cohomology class of phi and omega. So then if you run the type IIA flow using this perturbed initial data, the flow is still going to converge. But it doesn't necessarily converge to the reference structure, the stationary point you start with. It may converge to a possible different Ricci flat type IIA structure. And the next result is a result about formation of singularity. So in general, we are not expecting the flow to converge because this flow makes sense for any type IIA manifold with type IIA structure. Doesn't have to be Kahler. However, the stationary points must be Kahler. Okay, so if you run the flow on a non-Kahler manifold, then definitely you are not going to get convergence. And so in this result, we just analyze if the flow have short time, if the flow has a finite time singularity, what will happen? So we have to introduce some notation. So we let G be the associated Riemannian metric and Rm it's a Riemannian curvature tensor. We can also introduce this function U, which is the log of phi norm squared. This is a smooth function over the manifold. And our theorem says if the flow exists on a finite interval of time, and suppose within this time, the function U plus the norm of the curvature is bounded by a constant, then actually we can extend this flow a little bit. And the reason we don't need to put the absolute value on U it's because the lower bound is automatic. We can it's just bounded by the initial data. And this theorem simply says that if the flow develops a finite time singularity, then either the function U blows up or the curvature blows up. Okay, and moreover, along the flow, there's what's called Hitchins functional. It's actually monotonely non-decreasing. However, our flow is not the gradient flow of the Hitchins function. Okay, so these are the main results we proved. Any questions? Okay, so now let me explain some applications of our results. Yes.
Why did we restrict to type IIA? Does it generalize one restricted?
I guess type IIA case is quite interesting because this is the only case where in the symplectic geometry case. The other cases are we have complex geometry where we're evolving the Hermitian metric. Basically, those are like extensively studied, has been extensively studied before. But this symplectic case, I guess there's a less work in this direction. Yeah. And yeah, so and I just saw the pop-up, and the functional is, the Hitchins functional is smooth. Okay, so let me mention the first application. It's finding optimal almost complex structures. So, so already we see some results. We see the convergence in the integral case, but this is not a very interesting case because you know there's a Ricci flat Kahler metric. And we also have some examples that even you start with something non-integrable, but your manifold itself supports an integrable SU3 structure, you may still have convergence. At least we have some example like that on 6 torus. But what makes it more interesting is to study the flow on a non-Kahler but symplectic manifold. So a easy or a model for us is to run this flow on what's called a symplectic half-flat manifolds. And many of them are actually locally homogeneous. And we want to find, on these manifolds, we want to use our flow to find the optimal almost complex structures. So a symplectic half-flat structure in our language is just a type IIA structure with the extra condition that phi norm square is a constant. And many examples of such things are locally homogeneous of the form G over gamma, where G is a 6-dimensional Lie group, and gamma is a discrete subgroup such that the quotient is compact. So it's called a co-compact lattice. And both omega and phi, we want them to be left invariant closed differential forms. So they reduce to, they descend to the quotient G over gamma. Okay. And in this locally homogeneous setup, actually, we have more monotonicity formulas. We can show that this e to the minus u is its time derivative is non-positive. It's measured by the norm of the Eigenhuse tensor, which measures non-integrability of the almost complex structure. And moreover, the derivative of the Eigenhuse tensor norm square is also non-positive, and it's measured by the J anti-invariant part of the Ricci curvature. So a direct corollary of this monotonicity formulas is that suppose we start our flow with a locally homogeneous symplectic half-flat manifold of the form G over gamma, then this structure is also preserved. And if we further assume that the flow exists for all time, then actually along the flow, this family of almost complex structures, though they are not going to be integrable at any time, however, they can, an Eigenhuse tensor is convergent to 0. So you can make it arbitrarily small. So which means you can, in some sense, you can construct almost complex structures on such symplectic manifolds so that they can be arbitrarily close to a Kahler structure. However, you can never achieve it. And there are more such examples found by Fernandez, Xing, and Wilson, but they're using very algebraic constructions. Okay, and so this is a general statement asks for long time existence. And we have some very specific examples. The first example is a neo manifold constructed by de Bartolome and Tomasini. So here, neo manifold means the group is nilpotent. In this case, the flow does exist for all time. So the previous corollary applies. So we get a family of almost complex structure with arbitrary small Eigenhuse tensor. And I think the more interesting example is the example 2 here, where we work with a solved manifold constructed by Tomasiello and Tseng-Yau. So here G is solvable, but not nilpotent. In this case, the flow actually blows up in finite time because of the function U blows up. However, the curvature does not blow up. In fact, if you take the limit of the underlying almost complex structure, it exists. And you get something very nice. It's called a harmonic almost complex structure, which is also a minimizer in this case of the Eigenhughes tensor among all compatible invariant almost complex structures. Here, this harmonicity of the almost complex structure, this is a notion introduced by Le and Wang, and sometimes that's just called the Hermitian-Ricci tensor. So it's like if you have a symplectic manifold, this compatible almost complex structure is called harmonic if the associated Ricci curvature, this is the Riemannian-Ricci curvature, is J invariant. And of course, Kahler manifold, for Kahler manifolds, this is automatically satisfied, but in general, if it's not Kahler, it's still possible to find examples of such things. And more solutions of this types are studied by Raffaello. And in fact, we have more examples like example 2, for example, on some twistor spaces of hyperbolic form manifolds. Okay, so these are some examples where we can use our flow to find optimal almost complex structures. The second application is the one I stated at the very beginning. That is, we can use this to prove a symplectic version of the BTT, the Bogomolov-Tian-Todorov theorem. So the precise statement is that if we start with a compact Kahler Calabi-Yau threefold, M and the omega bar, then there exists some number K and the epsilon positive, such that for any symplectic form, omega, which is very close to our reference Kahler form in the WK2 Sobolev norm sense, then this symplectic manifold is also Kahler, which means it meets integrable complex structure that is compatible with it. And the main steps in proving this is the following. So since the thing we start with is a Kahler and a Calabi-Yau, it comes with a Ricci flat type IIA structure. And that is a stationary point of the type IIA flow. And then we show that we can upgrade a nearby symplectic structure to a nearby type IIA structure. So this thing, they are not unique. And we can show that we can choose this very carefully so that we have these estimates. So the arrow in the 3 form actually is bounded by the arrow of the symplectic form, the 2 form. So we can then we can run the type IIA flow using this nearby type IIA structure we find. And by the dynamic stability result, which we know using this as initial data, the flow will converge. And if the flow converges, it converges to a Ricci flat Kahler manifold, a Ricci flat Kahler structure, which the complex structure there is integrable. So which proves that, and that complex structure is compatible with our perturbed symplectic. So this is roughly the idea of this result, how we prove this result. And recently, using exactly the same idea as ours, Streets and Tian, they have an announcement that the same holds for Calabi-Yau in any dimension. So none. Okay. So. Okay, so I have 15 more minutes. So. Okay, so I guess I can now talk about something more technical. So that's about the proofs of certain results in our work. I want to start with this theorem A, that is about the short time existence and the uniqueness. And actually, this is a quite complicated proof. So this is our flow, and this flow If it's parabolic, then it's fine. Everything is automatic. But it is not. It's only weakly parabolic, similar to the case of a Ricci flow. But in some sense, it's worse than the case of Ricci flow. Because we know that usually there are two ways to deal with weak parabolic equations like Ricci flow. So there's Hamilton's Nash-Moser theorem, or there's a de Turck's trick. You can reparameterize the flow smartly to get a strictly parabolic equation. If you want to apply Hamilton's theorem, you need what's called an integrability operator. It's a first order operator. And in our case, we do have one. It's just the exterior derivative D, because we see the right-hand side of our flow is a closed, it's an exact form. It's in the kernel of this first order operator. So if you just apply this Hamilton theorem directly, you are restricting your symbol to the kernel of this integrability operator. But in our case, the symbol is still degenerate. So it's not good enough. You don't get short-time existence naively by applying Hamilton theorem. So then you can try the de Turck's trick, which is a way to reparameterize. Immediately you realize that our flow in our scenario, we fix the symplectic form. However, if you reparameterize the flow, then the symplectic form is also reparameterized. So which means it's going to change, but the vector field you use to reparameterize depends on the data of the evolving data. So this will actually make the symplectic form an unknown. And so in this case, if you are going to reparameterize, then you have to consider a coupled flow of the pair, the 3 form and 2 form. Okay, so here we can just consider the reparameterized flow, which is a coupled system of phi and omega. But so here the vector field V is a properly chosen de Turck type vector field. And but you'll see that this thing here is not good enough either. And we have to actually add something extra. That's the red term there. So the red term is a regularization of the reparameterized flow by V. And this term is expected to vanish. Without this red term, you can show that the probability is improved, but it's still, the symbol is still degenerate in the non-primitive directions. And we have to consider these directions because this is a coupled system. So you should treat phi and omega there as independent objects. So there is no a priori guarantee that along the flow, the pair stay a primitive pair. So you have to consider these this non-primitive directions. So we need to add this red term to deal with the non-primitive directions. And the red term fixes this degenerate directions. Okay. Okay, so the real thing we do is we consider this coupled flow where we have all these red terms. The other two with d phi and d omega, they are expected to be 0 because we expect the flow, the closeness to be preserved along the flow. So anyway, you can show that this flow is for this new flow, you can apply again the for this flow here, we apply, we don't get the full parabolicity. But for this flow, we can apply Hamilton's Nash-Moser theorem. We still have this integrability operator D because all the terms we add are exact terms. And so by applying Hamilton's theorem, we can show that this flow has short-time existence and uniqueness. And then we can add back this d phi and d omega term because this we're evolving closed form by exact forms, so it's still closed. And so the things we add on are 0. And then we get some lead derivative. Lie derivatives we reparameterize, we show that this triple star flow has short time existence and uniqueness. And we still have this red thing there. And then we use maximum principle to show that if initially this red term is 0, then it stays 0. So we get the short time existence of our. So that's the idea of the proof. And in summary, the proof goes like, okay, we have to first do a reparameterization to get a coupled flow. And then for the coupled flow, we have to do an extra regularization. And with the regularization, we can apply Hamilton's results. And then we come back and use maximal principle to prove the short time existence of the original flow. So the uniqueness can also be obtained this way, or alternatively, we can get the uniqueness by studying the induced flow of the associated metric G and U, and then apply Hamilton's theorem. And this alternative approach calls for a careful study of the type IIA geometry. So it's actually very interesting that in the case of type IIA structure, the almost compact structure there is very special. It's much more integrable compared to a generic compatible one. So you can show that there's a holonomic interpretation of the structure in SU3 with some other connection. And also the eigenhues tensor has more linear symmetries and it satisfies some quadratic identities and the differential equations, and also various curvature identities. So it's a lot of special properties about this geometry. And for example, in general, this eigenhues tensor has very many components in dimension 6. However, if this comes from a type IIA structure, you can show that it actually only has 6 independent components. And all these properties, they are useful to derive the evolution equation of the G and U. And this allows us to prove this continuation criterion by studying the flow of the pair G and U. So here, the G, if you look at the G and U, you are going to lose some information because originally you have a flow with 3 form, but algebraically you can rotate this 3 form by any angle. It doesn't change G and U. However, it turns out G and U, they together, they satisfy a closed system because everything on the right-hand side of this evolution equation depends only on G and U. But without the extra phase angle, you're losing. And you can recover the 3 form by solving a linear ODE whose coefficients are just comes from this pair G and U. So standard ODE theory tells you that the flow of the 3 form exists as long as the coupled flow of G and U exists. So we only need to do the estimates of this subsystem in the original, a one-dimensional bigger system. Okay, and then by using some of the special geometries and estimates, we can prove our results. Maybe let me skip this part for now. And now let me say something about the dynamical stability of the flow. So the way we prove this is to adapt and simplify the arguments of Natasha's system on stability of Ricci flow with integrability condition. The reason we need to do this is in other works, especially works about stability of Ricci flow, they always talk about the Perelman's functional. But in our flow, we don't have such a thing yet. So, so we have to use what's in Natasha's system's word. Okay, and so what we do is we have to work with this reparametrized type IIA flow. So we have this Ricci, so it's a deterg type vector field to help us. So our flow is like dt phi. Is this with this reparametrization? These are some second order operators of phi and omega. We call them E and F. And here I give the specific formula for the vector field. A natural thing to do is to compute the linearized operator. So at a stationary point. And because E and F, they both depend on phi and omega. When you linearize it, you'll get something depending on both phi and omega. But it turns out it's actually not coupled each other. If you restrict your deformations, if you restrict to deformations of type IIA structure, because if you have a type IIA structure, you have, omega and phi, they should be closed. So there's some, the deformation should also be closed. Also, you have this primitive condition, infinitesimal version of primitive condition that gives you some relation between the deformation of phi and deformation of omega. And by making use of all these relations, you can show that actually these linearized operators, they are decoupled. And they are just some constant times the Hodge-Laplacian operator, which is very nice. We know the spectrum, we know it has a sign. And this is really a very good starting point to prove the dynamical stability. And also, I think this computation also convinces us that there's a really nice geometric picture behind this flow. Okay, so basically this is because of the linearized operator, they are very nice. So this enables us to prove this dynamical stability result. And another point here is that though we know the flow is going to converge, but it doesn't necessarily converge to the stationary point we start with. And there's a whole moduli space there. And here we need to use a kind of implicit function theorem to find what exactly is the flow going, what's the stationary point the flow is going to converge. Okay. Okay, so now I can get back a little bit to these estimates. So to get this for these estimates, we have to use lots of geometry properties of type IIA structure. So what we assume is U is bounded and the curvature is bounded, and we want to show we can get all the higher order estimates. And there's some identities which I list, and using this identity, we show that the curvature bound actually implies that the eigenhuge tensor is already bounded in C0 sense, and also the J invariant part of the Hessian of U is bounded. And this is the key thing here, is the J invariant part of the Hessian is already bounded. And this is extremely useful when we want to do the C1 estimate. So we can compute this, we want to apply this maximum principle to this test function S, and we get this inequality. And the bad term here is the Hessian U, and we can use the good term, which is the first term, very negative term, to control it. If we just complete the square directly, then we get this thing. But the coefficient in front of a gradient U is always positive. So you cannot make it negative, and it's not, the maximum principle doesn't help us. So this naive attempt fails. However, there's a trick that is to use this J invariant part of the Hessian to have a better estimate. So that is, we already know the J invariant part is bounded, so we can break the Hessian U to the invariant part and anti-invariant part. And we only work with the anti-invariant part. And the same calculation there is that you have, because you are pairing the anti-invariant part with du tensor du there, but invariant part and anti-invariant part, they're orthogonal. So you only need to take the inner product with the anti-invariant part of du tensor du. And that improves this coefficient because the anti-invariant part, when you're completing square, it's only 1/2 of the original du tensor du. And that gives you a coefficient without quadratic term, which you can make it negative. And then the maximum principle works. So you get the C1 estimate. Okay, and I think now I should stop here.